So in this next part of the screencast, we'll just look at the different kind of compilation stages what go on. Because in this previous example we've seen, we've gone straight from the source file to create the executable file. But actually there's these kind of sub-processes what are going on. The first part of that is a preprocessor. So I'll just delete the main.exe file now, just so we can start from kind of complete scratch, if you will. So we've got the first stage, which is the preprocessor. So we can actually stop it after this preprocess stage by doing this -e. So I'll do -e main.cpp. And I'm going to run this now. You're going to see this. It's going to print tens of thousands of lines of code. So I'll stop. It's just dumping the file to the screen now. So I'm going to press Control and X to kill, Control C, sorry, to stop that. Because we can actually use, because obviously not good if it's just printing tens of thousands of lines to the screen. You can't really see it. So if we put that kind of that symbol in, we can kind of pipe the output to a file. So I'll call this main2.cpp. So now it's, instead of printing all that text to the screen, it's printed to this file. So in Notepad++, I can open that file, and we can just quickly look at this. And basically what it's done, because in our original source file, we have this #include IO stream. So all the code, what's inside it's basically took all the code what was inside this IO stream class and put it inside this source file. So this is now all the contents of IO stream essentially. So you can see it's a very big class. And then at the very end, so you see 24,000 lines of code here. So you can see then at the very end, we just got our main function what we had. So all this is just kind of expanded IO stream and put it inside this main.2cpp. So that's the kind of preprocessor. So that's taking, if you've got some libraries, so iostream.h for example, it just puts it inside of your source file. So now this is the kind of result of this preprocess stage, for example. And we could just do the same. So I'll call it main.exe again. And now do main2.cpp, compile that, run it, and we've got hello world. So that's the kind of preprocessor. We'll have to do another example just to make it a bit clearer. So again, I'll remove main2.cpp, and I'll remove main.exe. And we'll just delete this. So we won't be able to see the output. We won't be able to print to the screen because we're not going to use IOStream. But there's another preprocessor directive called define. So you could do #define. Because this can be useful if, say, you want to use pi. So you can define pi. So we normally use uppercase for the labels for these preprocessor directories. You can put 3.1415. You can put the value of pi in there, and then in your code then. So we can't use int for this because it's a floating point numbers. So I'll just do float x equals pi. So I'll just save this. So now it's not going to pull in all IO streams, so I'll run the compile command again, but with an E flag, so that'll tell it to stop after the preprocessor stage. So we can see now that's basically gone through. It's almost like a copy, like a find and replace type thing. So when you do define, what the preprocessor does, it look through your source file, and every time it comes across pi, what we defined here, it'll replace it by this. So it'll find all instances of pi and it replaced by these numbers. So we can see in this example here, we've got our main function here, but rather than saying float x equals pi, it now says float x equals 3.1415. So it's just a preprocessor. It's not compiled anything. It's just modified the actual source file. So that that's this kind of preprocess stage. I'll add in a couple of variables as well. So I'll do int So we've got a variable, call it A, we'll give it the value 5, int B, whatever, give it value 3, then we'll do int C equals A plus B. So again, this is not going to print anything out because I'm not include IO stream, so we can't use C8 to print anything. But I'll just, that'll come in useful for what we're going to show next. So here we can see we've got our, after the preprocessor, you know, this is a result here. So after the preprocessor, the next step, what takes place is the assembly. So this is where it kind of converts our C++ code into the assembly code for that particular platform. So depending if you're on a PC, with an depending on the instruction set architecture, for if you're on a PC or you're on a writing code for microcontroller, it'll convert the C++ into the actual kind of assembly commands for that particular architecture. So we do that, we invoke that step by doing -s. So now this will do the preprocessor, it'll do the assembly, then it'll stop then. So I run that command and do ls. So now we can see we've got this main.s file. So I'll open that in here. So you can see that's picked it up now as an assembler source. So if we open that, so we know the bits at the top here, but we can start seeing some of the actual compile commands. So this is our kind of high-level C++ code. It actually gets converted to this kind of low-level assembly code. So for example, these lines of code here, we've got int A equals 5, int B equals 3. So we can see these here. So this is moving a literal value. So this is our literal value 5. It'll move it to, because a variable is just like a memory, is just a location in memory. So it's just moving those literal values to memory locations. So you can see these are multiples of 4. So I've got location 4, 8. So that's because an int is 4 bytes, it's 32 bits. So that gives us 4 bytes. So each integer takes up 4 slots in memory. So the actual slots where you save them will have to be multiples of 4. So we got those literals, and you can start to extract out. Then you can see here we've got int C equals A plus B. So this is this add. You can see this is this add command. So we'll be adding the two values together. So for example, if I did another one, so I did int D equals A minus B, for example, and then int E equals A times B. So let's save that. I'll go back. That will reassemble that. So now you can see. So in C and C++, when you do this kind of add operator, that corresponds to add L instruction from the kind of Intel instruction set. And minus, that's this sub, and then multiplication, this imul. I may as well add it in just to see. Int S equals A divided by B. Just save that. Do the same again. And check. You can see idiv out. So we've got, so the next step of the compilation process is converting this source file to this kind of assembly code. So at that point then we've got this main.s. So the step after that is when we convert that into the object code. So this is where it actually gets compiled. So I'll do G++. So we do that using -C. This is the kind of compile flag. So so the first step, so this -s has kind of done the assembly step. We've got our main source file. Now with this C flag, I can convert this source file. If I run that command and do ls, you see now we've got the object file. So this object file is a kind of, the ones and zeros, because we can't open up the object file. it just gives you all this kind of junk here. So this is not a text. This is no longer kind of a text file, if you will. You know, this is a compiled object file, so we can use. You haven't got Hexedit installed, so you can use these hex editors. What can open up these files? So if we open up main.o, you can actually see the kind of binary values. So these are the displayed in hex, if you will, but these are the kind of raw ones and zeros. So this is kind of showing the ASCII equivalent. So we compiled that source code into this binary machine code or object code, and this is the kind of raw ones and zeros which will be copied in, which are kind of copied into the memory. These are the actual instructions that are executed. So that's in main.o. And the very, very final step is just to link that with library files as well, apart from the C++ library. So from here, I'll do ls. So I'm going to do G++. So this is that last step. So that -o, we'll call it main.exe. So that'll then link. This will just invoke the linker. And it'll link the main.object file with all of the library files to give us this main.exe. That's here. We've kind of gone through each step of this compilation process and everything. Okay, we didn't put any in our source file. We didn't have any print command, so we won't print anything here. So that's the code that will get executed now. So we've kind of gone from C source file to the assembler, so the binary object code, and linking that then with the various library functions to give us our executable. I'll just see that can open up, because you can see that this main.o isn't that big. It's only got just off one screen, but now if I open up the actual main.exe, so you can see this is actually much bigger once that's been linked with all the other kind of files that are needed to actually execute the machine. So you can see it's got to much bigger. So it can actually do ls, I think -l, and that tells us the file size of things. So you can actually see it. A main.cpp file, a raw CPP file, is actually 150 bytes, so it's very small. That's actually, when it's been compiled, it's actually converted to nearly 42 kilobytes. So you can just see that the extra file size from this kind of linking stage. So the main object file, say 840 bytes. And once that's been linked with all the things that's needed to create the executable, it jumps onto nearly 42,000 kilobytes. So this is showing each of the individual compilation steps, but we don't normally do this. You normally would just go directly from. So at this stage here, if you just replace that main.cpp, that will just do all the processes. It'll start from the CPP file, it'll assemble it, it'll then compile it, and it'll link it all in kind of one step. So this is a normal. Let's see. Also, it can't compile on this exe. I presume it's probably I've got it open in this program. So I'll try that again. Yeah, it's work fine now. So you normally just do the compilation in one step, but you can, if you want to, you can stop it at each of the kind of sub-process to inspect the files that are created.